All right, I want to thank everyone for attending our presentation today. The topic today is going to be electromagnetic fields. So understanding electromagnetic field requirements for transmission projects, including modeling, compliance, and mitigation. Just a quick review of our outline of what we're going to cover today. We're going to do introductions of the presenting team. We're going to talk about electromagnetic field EMF background, what input data we need for developing our models for our software analysis, some example results. We're going to discuss the limits and the guidelines nationally of how this can affect you in your projects, and also talk about mitigation methods, and then end with a Q&A session. Okay. So just a couple quick introductions. Myself, I am Ian Hutt. Just a little bit about myself. I have 2 degrees from Central Michigan University, electrical engineering, and a bachelor's in business management. I have over 20 years of studies, topics experience at Commonwealth and at other locations as well. I'm licensed in 7 states, including coast to coast, Alaska to Florida. So kind of neat. I have publications, multiple publications and presentations on EMF and other studies related topics across the industry. And just a neat fun fact is I've been able to have the opportunity to act as an expert witness for EMF on transmission projects in New York.
Hi, everyone. I'm William Turkovich. I went to school at Michigan Tech, and I graduated in 2020 with an electrical engineering degree and electrical power engineering concentration. I've been at Commonwealth for over 5 years, working in various studies topics, and I am professionally licensed in the state of Michigan. Just to get a gauge where everyone's at, we have a quick poll question, and it's how much knowledge do you have in electromagnetic field related topics? A, I've never heard of EMF. B, I may have heard of EMF in college. C, I have worked with some EMF concepts on previous projects. Or D, I work with EMF frequently and understand the concepts well. There should be a poll popping up.
We've got about 24 responses. We'll get wait one more moment here. Okay, here are our answers.
All right, so we actually have 0. I've never heard of EMF before. And it looks like most everyone in this chat is I may have heard of it in college, or I've worked with it on previous projects. So that's cool. And a couple 15%, I work with it very frequently. So I like that mix. Okay. So we'll go through some EMF background if you're in that B category and would appreciate it. So what is an electromagnetic field? There's 2 kinds. They're always in pairs. There's electromagnetic fields are driven by moving charge or a moving current, and then electrostatic fields are driven by a static charge driven by voltage. These fields exist everywhere around a current carrying conductor, including transmission lines. They're always together. An alternating electric field, an AC signal, will always induce a magnetic field and vice versa. An alternating magnetic field will induce a current in an electric field. What specifically is an electric field? It's just a measurement between 2 points in space of the potential between those 2 points. The common limits are volts per meter. They can be in newtons per coulomb, but they're mostly noted as volts per meter. What can electric fields do? They can induce a voltage on an ungrounded metallic object and have an induced shock effect. So in the picture on the top left, you can see an electric field that's standard. Once you introduce a metal sphere then all the charge within a matter of nanoseconds will shift to each opposing side. The same thing can happen to you if you're underneath an electric field, like a transmission line, and you touch a magnetic object, like a truck or a fence or anything else. And in the bottom picture, you can see how that affects. The truck will act as a grounded capacitor, and then you will add the path to ground, producing a current and completing the circuit. This is limited because you want not to notice that. It's also a reason why they have insulated shoes when you're working with equipment in electric field stations. What is a magnetic field? It's a measure of magnetic forces in that area. If you remember back to college, you can use your right hand rule. You can put your thumb in the direction of the current that's traveling, and you can curl your fingers around that conductor, and it will tell you which way the magnetic field is rotating. That will show you how it will induce current and the direction of the induced current on other metallic objects. You can see that the units are amps per meter. They also have Teslas or milligauss. Milligauss is the most commonly used for standards and recommendations. And you can see with the simplified equation, both magnetic field and electric fields are determined by the current or voltage and divided by the distance away from that energized object. So the higher the current, the higher the magnetic field, or the farther away, the lower the magnetic field. And then Ian will take this slide.
Sure. Just talking about how this can affect the real world a little bit. So when we talk about magnetic fields and electric fields, we have to consider transmission lines and how it affects other things. So in particular, of great concern is how these fields affect pipelines and rail lines, and what the impacts can be. Also, fencing. So the real impact is whenever we have parallel structures. So when the transmission line is running parallel to the rail or to the pipeline or say an adjacent fence. On the fence, depending on the fence conductors or the composition, we can have different impacts, and you can induce a current or a voltage on that fence, which, as we can imagine, can be pretty dangerous, possibly, especially if that fence is something that is not within a protected work zone. So, for example, outside of the right of way of the transmission line, where maybe the public may interface with that fence. So that's something we keep an eye on. We can do electric field studies to determine what we expect those touch potentials might be. If we deem them to be dangerous, we can talk about mitigation methods, grounding that fence, changing its materials to improve safety. When it comes to like pipelines and rail in general, now rail has had some pretty decent advances in their signaling, so it doesn't affect all rail lines, but in general, we can potentially affect the signaling on rail lines. We can also, when you're going to a crossing, it's watching where that train's at, and there's especially the older technologies are using that short trail. The wheels of the train, the axle of the train will short out the lines, and it'll detect the signal and tell the signal's going to operate. If you have a parallel transmission line, there could be interference from electromagnetic forces that affects that signaling. For both rail and pipelines, we always have the concern of affecting the cathodic protection on the metal for both the rail and for the pipeline, more specifically in the pipeline area. So we can look at that to see if that induced current that we're applying to this pipeline has any impact on that, because we want to make sure that we're not causing that cathodic protection to fail and causing corrosion in that pipeline that's unexpected.
One other thing to consider is if you are putting up a transmission line, the utility that owns that right of way may have an overlapping right of way with the railroad or the pipeline, and they might not be the same company, but they're sharing a space. Meaning, if you have an existing pipeline, you would have skin in the game to know if your pipeline is being energized with that electromagnetic field. And they say, just a little fun fact, a typical person can sense about 1 milliamp of current going through their body if they touch a current conducting pipeline. About 15 milliamps is considered painful, and it triggers a reaction with the muscles in your body that you can't release that object. So these workers and the owners of these pipelines have real reasons to look into your project. Maybe it's not the same company, but that can cause some conflict that we've seen in the past. So slightly different concept. What is a transposed pole or line? So a transposed pole is you have a three-phase line, A, B, and C, or in this picture, red, yellow, blue. Each phase is the same magnitude, whether that's 34.5 kV or 69 kV or 230, but they have different phase angles. These phase angles means there's different inductive and capacitive coupling that happens between them to cause a different impedance seen by each phase over the course of a long transmission line. To counter that, there's a separation, and they swap the phases like the picture in the top right, so that evenly over 1/3 for 3 different phases, they're experiencing the same overall impedance at the end of the line. This is usually only done for super long lines that you can pick up a difference of impedance. And it can be done at different voltages as well. Okay. So we have another poll question for you guys. Question 2, when should you question any metallic objects near a power line? A, when they're parallel to the line, B, when they're perpendicular to the line, C, when they're really far away from the line, or D, when they're really close to the line, or E, A, and D are correct.
Right, the poll is up. Have about 23 respondents. We'll wait just a few more moments. And still some more coming in, but it looks like we're sitting pretty good on that A and D response.
And you guys would be right. So when we covered the electric and magnetic fields, I said that it's really a distance function that that determines the severity of each field. The farther away you are, the smaller the values, meaning the closer you are, the more you should question what the values actually are. And when they're parallel is when those objects can be induced current and voltage-wise. So A and D was the right answer. Next, we're going to go through some modeling data inputs we'll need if we do a study. First would be if we do an EMF study on a transmission line. So what are the types of things we're looking for when we start the project? We need simple things like line voltage. That's an easy one. This is 345 kV line. The next one might be a little harder to find out. It's how far the easement or the right-of-way width is. In this picture, you can see it's 125 feet across. The next is the geometry of the poles and where the conductors are relative to each other, relative to the ground, relative to the optical ground wire above them. The next is probably the most difficult to gather. It's the maximum line loadings. This is the amount of current going through those lines at any moment and the highest value of them all. An example would be the summer emergency rating, meaning everyone has their AC on in the summer and all the transmission lines are maybe overloaded for a certain degree of time. That might be the worst one. The winter might also be worse. So you have to look at all of them and figure out which one is the maximum, because the higher the currents going through the lines, the higher the magnetic field. Some other data inputs are the number of conductors per bundle. So as an example on the right, we have a dual conductor 795 Drake. The conductor size is also important. The geometry of these cables has a big impact on what the EMF will determine. The optical ground wire ahead that protects the transmission lines from lightning strikes and can provide a communication path if designed that way. And then one of the more important data we need is the minimum height off the ground. So the picture on the bottom left shows a transmission line going across a bumpy terrain, we'll say. The line sags, and you can see that there's a minimum point that's closer or farther from the ground where the lines are. We need to find that point because, as we said, both of these fields are distance driven, meaning the closer they are, the more severe our results will be. You can see we have a max, a min, and an average height for these clearances. We can run all three. It will be the minimum as the most severe for both cases, but it's good to see all the different scenarios. Let's say you are running a transmission line, and what does the transmission line go to? It goes to a substation. Maybe it's a collector station for a wind farm or a solar farm. What do you need for that? We can do an EMF analysis of that. We'll need the conductor sizes, the tubes, how thick they are going from each piece of equipment, the voltage levels of the equipment, the transformer size, the breaker size, the collector buses and breakers. We need the general arrangement. So on the top right, you can see this example has 3 transformers connected to 3 breakers connected to the collector system and going out to a 3-phase line on the top of the screen. And then you need a side profile to 3-dimensionally describe what the characteristics of the substation are. So you can see how tall the breakers, where these wires are relative to the ground, where they are relative to each other. All of these different details add into how these cables play with each other with inductive and capacitive coupling. Another thing you might want to know is the fence location. How much land is considered yours for the station design? Where are people, the public, the general public, going to be restricted from? Because those are the people you want to watch out for, is the people who are not prepared for an electrical environment, who may be in danger if they don't know. Another data would be the maximum loading of the equipment. So what is the currents going through these transformers and breakers? That's going to determine how severe the magnetic field is. We need to know these things before going in, and then we can do some modeling of it. Once we do that, we can get some EMF basic results, assuming certain standards or typical values. And then Ian's going to go over some of these example results.
Sure. So we're going to start with looking at the transmission line EMF first. So what we're looking at is possibly a single transmission line that is going down a right of way. There's different things that can affect this. So like we mentioned earlier, the geometry of the conductors is important. So nowadays we see pretty common that we'll see steel structures. We'll see things like delta configurations with davit arms. Sometimes you get a vertical configuration. Sometimes it's centered at the right of way. Sometimes it's offset depending on the line characteristics as well. And and we still have options for other structures as well. So we can work with lattice towers. We can look at H-frames, whatever's out there. We're able to calculate and find out what the impacts are. Different structures are going to have an effect on this. The phasing, especially if we have multiple circuits. So if you have 2 circuits on vertical, steel pole, davit arms, vertical structures, you're going to see very different EMF results for an ABC top-down approach as opposed to an ABC CBA phasing. And there's other variations of that too that we can investigate. What we'll see with those results is that you're going to have a couple of things that are of note. We want to understand where we are for maximum values. Certain states, certain requirements limit the top maximum electric field values that you can have. This is going to affect people and workers that are within that right of way themselves, specifically at the minimum heights, the minimum sag points, as William described. Also, we focus at the edge of the right of way. Generally, we anticipate the edge of the right of way is where we may possibly interact with the public. This may be adjacent landowners, this may be houses, apartment buildings, fences, and things like that may be at or near the edge of right of ways. So we try to show that, especially with our graphs. We try to also show where the limits are. In this particular example, we're seeing that our limits are at 1 kilovolt per meter. And we can see that based on this analysis in this particular example for electric field, that we're below that limit. We're coming in at about 0.5 kilovolts per meter. So we're below the limit for our edge of right-of-way values. You can also see for this example that we're at about 2 kilovolts per meter for our peaks. So what we can see too is once we look at this, we need to understand really what's the point of reference. And what we'll find is when we look at electric field, if you're right at ground, essentially you have no electric field because you're at the Earth's 0 point. So we need to look at some distance above ground as our measurement point. By convention, we typically look at 1 meter above the ground. And that seems arbitrary. Like why pick 1 meter? That seems weird. Why not 2 meters? Why not look at it, the height of a person or something? The convention is we pick 1 meter because generally if you're going to reach out and touch something for an average person, average height, that's usually around about 1 meter off the ground where you might reach out and grab something. That might be a fence, like that earlier example. That might be like a vehicle that's in the right of way or near the edge of the right of way. And we're really kind of looking at where that induced voltage might be and where that touch potential may be. So that's kind of why we tend to focus at that height. And like we mentioned before, it's a distance squared function. So the closer we get to the zener conductors, generally the greater we're going to see the magnitude of that field. And one more thing to note, when we look at these cross sections, we're kind of assuming that the right of way itself is generally flat and graded. And we all know, if we've had the experience with transmission lines, that's definitely not always the case. So whenever we look at a site, we tend to focus at the edge of right of way. And if we know that, say, there's a slope across this right of way where one side is higher than the other, we're going to try to find the minimum distance to conductor that is likely for the scenario, and that's where we're going to make our origin point. So we tend to be conservative to make sure that we come up with conservative results when we do this analysis, and that we're going to err on the side of caution for protecting workers and the public.
One other thing about being conservative is one of the baked-in assumptions that we use is there's a certain voltage difference that transmission lines can operate at on a daily basis, continuous, not being tripped off by protection. This specific example was ran at 105% voltage, because in that specific utility, you can see it will continuously run at 105 to 0.95 voltage. The electric fields are directly related to the voltage, so that's just another example of how we can bake conservativeness into these projects to add that protective value.
So this is neat too. We wanted to show just how loading can affect magnetic field values. And this is a neat graphic to take a look at. So like William mentioned, the magnetic field is directly proportional to the loading. So there's a couple of ways that we can look at it. So many transmission lines don't ever get loaded to their maximums. They tend to operate at some smaller value there, but they have the potential to go to their maximum values. Depending on state and state requirements, we may have to look at those conductor ratings when determining magnetic field levels. Sometimes we can use actual loadings. So it just depends on the scenario and the situation, what value we use. Because generally the rating itself is going to be much more severe than an actual loading, it tends to give us more severe results. And this is a nice example of exactly that here. So as we kind of look at these different graphs and colors, we can see everything from a summer normal rating to a winter normal rating, all the way up to the summer emergency and the winter emergency ratings. So we can see that in this particular scenario and case, that winter emergency rating is our peak. And it's giving us very severe magnetic field levels because we can put more current on that line. The ambient temperatures are cooler, so your sag and your conductor temperatures are going to be a little bit less. So your sag limits won't be exceeded here. So, but because those loadings and that current level is up, we're seeing that the magnetic field level corresponds accordingly and also goes up. And so it's a nice example here to show that, hey, that loading level is going to be directly proportional to the magnetic field peaks. And we can see impacts both on peak magnetic field, where we're coming in at just over 100 milligauss for the worst case scenario winter emergency rating, which is not quite double, but near what it is for a summer normal rating. So that's interesting. We can also look at the edge of right of way, that just because of the structure, the characteristics of the transmission line, we can see that we have a pretty good slope off once we get towards the edge of that right of way. You can see that once we get to the edge, because this is a distance squared function, as you move away from the center line of the structure, that our magnetic field levels drop considerably. We're hovering even, best case scenario around, say, 17 milligauss, and then worst case scenario, maybe around 21, 22.
One thing I would also note would be you can see the bars that show the edge of the right of way, but we've also plotted and calculated far beyond that, up to 500 feet total in this example. And maybe you're a utility that's making a line and there's a person who has a house 125 feet from the center line of your line, and they're concerned about the electric or magnetic fields affecting them. When we run the study, we have that extra data to show them exactly how much those levels are relative to safety limits, and maybe be able to add some comfortability to that answer for that concerned person. This slide is one of my favorites. If there's any physical or civil people who don't really know EMFs, this is one of my favorite pictures to look at. It's a three-dimensional, and then the left picture is a color-graded graph of a substation, and you can physically see how the EMF is affected. Both these cases are electric field by the equipment themselves. You can see that tall peak is the transformers because the voltage is the highest, directly affecting the electric field. You can see they're getting closer together the higher the peak is. You can see there's another little spike where the breakers are, and those conductors are getting really close together despite their typical distance separations. You can see where the high voltage lines come together. There's a couple hot spots there. And then you can also see how horizontally at the fence line, maybe you're on the south facing fence, that X axis, you can see how low those levels are too. I appreciate looking at these graphs visually. Then here's another way of displaying that graph, would just be two-dimensional on the left screen. You can compare it to the right to kind of put the pieces together. You can still see, maybe you compare the left graph to your side profile of your substation, and you say, okay, I can visually see this is the transformer, that's the connection tie, that's the breaker, here's the collector station, here are the peaks in volts per meter. We're seeing a super high peak around 4,400 volts, 4.4 kV per meter at those transformer high sides.
One thing to note too, and we're seeing this as we do more and more of the renewable collector stations, which could be, BESS or solar or wind. Once you generally have an underground medium voltage network that's going to say a array of solar PV and inverters, or to wind towers, or possibly in a battery yard. Those underground cables are coming up and into your breakers. We actually see a fairly large impact for those cable risers as well, those insulated cable risers on the EMF side. So whenever you have a station that's tight with a very limited fence, there may be potential EMF concerns that maybe are unexpected when we talk about those cable risers. So just a neat piece of information to glean from this, and something from our experience that is of note.
Mm-hmm. So let's say we've ran all those studies and we know the current site specifications. What do those numbers mean, and how do they actually affect you? Well, if you live in any of these 4 states or under the jurisdiction of the last 3 organizations, they'll limit you in electric field limit. This is at the edge of the right-of-ways, either of them. You can see states like Florida, Montana, New Jersey, or New York have limits. These were all laws passed around the 80s when there was a couple medical journals that had some studies published that claimed EMF values are affecting children with leukemia. So these states were the first to adopt certain limits. Since then, some of those studies have been disproven. But these limits are still in place and still applicable to any transmission lines or substations in those states. You can see the highest is New Jersey at 3 kV per meter, or Montana that's at 1.0 kV per meter, the most conservative state in the US, Montana, for electric fields. Now, if you got magnetic fields, you can see this graph is greatly skewed. There's only 2 states on this graph, Florida and New York, at 150 and 200 milligauss. That's the magnetic field, one of the units we use. And then there's ACGH, GIH is 10,000 milligauss. You may say, why is that so different? That's actually the American Conference of Government Industrial Hygienists. And they've determined that 10,000 is the maximum limit for safe occupational usage. We could see the Florida and New York are way below that. That's just an interesting piece of data that different organizations have different values depending on which jurisdiction you're currently in can affect you greatly. Now, maybe you're in a different state that doesn't have one of these limits. You can at least compare it to Florida and say, well, we're better than Florida. We're better than the most conservative limit in the US. Right. We have another question. Question number 3. Might be a little cheap because I didn't tell you briefly. Is the example below within the strictest limits above? So we've got an electric maximum at the edge of right-of-way of 0.51 kV per meter. And we've got a magnetic maximum at the edge of right-of-way at 183.7 milligauss. Option A, the electric field is within the limits. Option B, the magnetic field is within the limits. C, the electric field is not within the limits. D, the magnetic field is not within the limits. E, A and B are correct. F, A and D are correct. So we'll put a poll up real quick.
You've got about 9 or so responses coming in. We'll end it in a few more moments. Okay, it looks like it's about 18 for now, William. So here you go.
Okay, I'm looking and we have a mixed bag. We've got 60% are saying A and D, a couple in A and B, and a couple in the electric field is not within the limits. The correct answer is A and D. So before we said the most strict state across the United States is Montana with an electric maximum field of 1.0 kV per meter. And the most conservative state was Florida at 150. So the magnetic field would not be within the limits of that most strictest criteria, but the electric field would be. Now you may ask, well, I'm in Ohio or I'm in Indiana. You didn't say anything about those numbers. They don't have formal limits set. Some of them have local occupational precedents. We'll look into those, but the benchmark is if you're within the strictest states, then you're pretty good and it won't really affect your scope, schedule, or budget of the project. Let's say you're not within any of those values and you are in a state that actually requires them. What can you do about it? So there's 3 mitigation methods we commonly recommend. You can change the phasing of the conductors, you can change the geometry of the conductors, or you can physically change the height of your transmission poles. The first one would be easy. Change the phases. All it is routing the conductors in a different order than what you were planning. It doesn't change any different cables, just changes the terminations at the very end of the lines and any tap lines in between. It's relatively easy. It can improve electric and magnetic fields like the graph on the right side. You can actually see it changes the shape and the magnitude of these fields in both electric and magnetic fields, but that's not guaranteed depending on the different characteristics. And all you're doing is just changing the different conductors. The only catch with changing the phases is, back to the beginning, what if this is a transposed line? What if this is ABC down on both conductors, but then a third of the way down it changes to ACB or CBA? Then a third of your line is always above your limits. That doesn't help you. What can you do then? You can change some of the geometric conductor configurations. That's a lot more expensive. It can change and reduce the EMF properties. It's not guaranteed. It takes a lot of more planning with long lead items, such as the arms of the poles. They can't support that change you're talking about. On the left, you can see a double vertical structure. You can change that. If it was a vertical structure, you can change it to dual vertical. Or if you're right, you can do the delta structure and change that geometry. These will all have different shapes and magnitudes. Ian will pick up the next slide.
Sure. Yeah. So the geometry is a big play on how the phases interface with each other, and it's always a balancing game. So you have minimum spacing that you are required for open outdoor air insulated conductors, right? So there's only so far away or so close that you can keep these conductors, and that arrangement is important. Generally, if we can get the conductors a little bit closer together, sometimes you can have cancellation effects that can greatly help you on the EMF side. Also, what you can find too is as you get those conductors closer together, you may have a higher peak, but maybe it falls off more drastically once we get towards the edge of the right of way, which can be a beneficial property. So this can be affected by a couple of things. So when we talk about conductors and conductor spacing, there may be standard equipment out there or utility standards. So, these insulators may be a standard size. We may be able to go to a shorter or a longer insulator if that's a possibility. But then we get into this world of non-standard equipment. It's more difficult to maintain. So there's always challenges with that. Also, just talking about the structure types. So different structure types generally have inherent different EMF properties. So what we see here in the picture is a standard H-frame. So these H-frame structures, and these can be steel, these can be wood, different voltages and different loadings of conductors plus multiple strands per circuit or per phase can affect the required structure requirements. But if we look at an H-frame in particular, they generally have a wider profile when it comes to EMF, and usually a little bit less on the peak. So if you're looking to go with H-frame structure and you have a narrow right of way and EMF is a concern, it may not be your best choice. And that's something that's maybe difficult. So with the EMF, we generally get more involved towards the end of projects. This makes a case to maybe take a look at EMF, especially if we know that it may be a concern coming up in states that have strict requirements, particularly like New York and Florida, possibly Montana, that you want to maybe get a look at this early and look at different structure types, and that may go into your design. So what we can see here with the H-frame, we tend to have a very wide profile. When we get into things like the vertical and double vertical structures, generally we have a higher peak value, all things being equal, with the same conductor, same loading, same voltage levels. But it tends to drop off very quickly towards the center, towards once you get over to the edge of the right of way. So if you have edge of right of way requirements that are strict, and you're looking to find a structure or a type that works well in that situation, that may be your preferred. Some states also have maximum values. We didn't get into it too much here, but depending on the state and the requirements, you may have to limit your maximum peak values as well. So again, it can be a kind of a trade-off, right? So if we're looking at the vertical structures or a delta structure that tends to have the high peak, so maybe we bounce off that top limit, even though we have really good edge right-of-way performance, it's less than ideal when it comes to maximums and peaks. What we can find too is when we go to like a double vertical, and you have the two circuits, and you have those circuits phased opposite. So CBA top to bottom, and then ABC top to bottom. We tend to get a lot of cancellation with that. That's really nice. What that'll do is that'll knock that top peak down considerably on your magnetic field and electric field levels, but it kind of pushes that electric field out towards the edge of the right of way. You can kind of see that with that orange kind of camel hump drawing there in the middle. as you can see that the difference is that the yellow, which is the vertical structure with a single conductor on it, has kind of peak performance, but it's very nice performance at the edge of right away. As we go to that double vertical and we have that cross phasing, we get that real nice cancellation that happens in the middle, which is very nice for mitigating peak values. But you can also see that it kind of pushes that electric and magnetic field out towards the edge of right away. In this case, the electric field. Another thing we can talk about is this is all of the EMF is a distance squared function. So the farther and farther away we get, the farther and farther that those electric and magnetic field values drop, and that works for both cases. So we always look at the minimum sag heights, and generally those minimum sag heights are your worst case. If we know that we have pretty strong EMFs that are braking requirements, there's always the solution to possibly go taller. So if we can get those sags raised, those towers raised, or if there's a particular landowner or a concerned party that has a very high value for EMF, or there's concerns there, sometimes they can be mitigated with structure height changes. Now, we talked about cost. I mean, this is generally one of the more expensive options to deal with. You know, raising pole heights can be challenging, especially if we're later in design and poles have already been ordered. There's some tricks that we can use, so you can increase the height of your foundations. Sometimes you can add more fill to raise that height. Again, there's other considerations there. If you have a very tall foundation with a whole lot of reveal, it may be challenging for installation and maintenance. Again, there's cost considerations for ordering taller steel poles. There may be limits to what height poles are even available to make this work. But it is one tool in our toolbox to understand how to possibly mitigate EMF when it becomes a major issue. And again, when we talk about today's environment, right? Lead time is everything. If we can find ways to get ahead of it, that's always great. You know, when it comes to steel, usually that has to be one of those things that gets ordered in advance, sometimes before all the engineering is complete, and very likely before EMF studies have happened. So another thought is maybe looking at preliminary design, preliminary EMF analysis, just to make sure things are fine, especially if you're in an area that might have concerns. Generally, that tends to be areas that have strict limits, that has very narrow right-of-ways, and then see if we can find ways to get ahead of the problem. Generally, if we have to go to mitigation techniques like raising poles or raising foundations, we'd like to do that earlier than later, or look at other options. Maybe there's a route with more right-of-way potentially that would be a better choice, or maybe we can look at phasing changes simply to address these issues. So there's always a couple things in our toolbox that can help us mitigate these problems and find ways to get your project to be successful. All right. Well, thank you everyone for attending the call. I'm going to open up the Q&A. So if you want to put your questions in the chat, we'll do our best to field those questions, or let you know if we can reach back to you after the discussion with additional information.
Yeah, we do have mics on, I think, if people want to ask their question verbally. We also have the Q&A app, which there are no questions. There was a comment I'll get to from, let me scroll and find it, from Christopher Soderman, talking about how I think the NY guide is not necessarily a hard restriction. This is talking about the chart with the Florida, New York, just some of that other data. And then it says the New York guideline was based on no increase principle, I understand. So it looks like questions, comments around how those things are created and like what do they actually mean and why would they be so different?
Sure. I can fill this one if that's okay, William.
Mm-hmm.
So I've done quite a bit of work in New York on EMF. And you're right, Chris, I think, Christopher, that I think that's a guideline. However, it's a guideline that's adhered to pretty severely by the Public Service Commission in New York. So I've been involved with a number of Article 7 permitting applications for transmission lines over the years. And I've had the opportunity to act as an expert witness in New York to discuss those things. So what I found, at least from experience, is that that guide, I believe it's like a 1976 or 77 guideline that was published, is still kind of the ongoing limit in New York, and it's very restrictive. And whenever there's a Article 7 application, we are very likely going to be expected to meet or beat that with EMF requirements. Now, there may be exceptions to that rule. And again, I can't talk about all projects, but the ones that I've been involved in, the utility has gone through great lengths to make sure that they applied mitigation techniques to meet those requirements in New York. So that's been a challenging one there. Now, mind you, you're right. I think that is just a guideline, is how that was published and what's going on there. So I don't think there's like a law that is being like enforced there. It's not something from IEEE or from OSHA or something like that, but it does come up quite frequently with the Public Service Commission and getting through that Article 7 process, at least historically. And then I think you had a follow-up on that too. What was your follow-up here? Is the no increase principle. So a lot of times with transmission, you're maybe reconductoring or replacing existing structures and towers. And that is something that usually comes up is, okay, so what if the old structure was built before that guideline was released, or maybe there's an exception to that guideline done on that structure or those series of structures? That is always an argument you can make in those Article 7 discussions, because again, it is just a guideline that we're trying to meet. But again, back to my experience working in New York, is that the utilities are heavily vested in meeting that standard and that guideline. And we'll go through great lengths and incur great costs to make sure that's the case, to get through that Article 7 process. So that's kind of where my thoughts are on that topic.
Thanks, Ian. Got a couple more in here. Another from Christopher, follow-up, probably for William on this one, but what software do you use for EMF calculations?
Yeah, we primarily use CDEGS. There's a couple modules we use for transmission lines. We do Trallen. And then for the substation, we found the high frequency module performs pretty well for that data analysis. So CDEGS, it's a SES product. It's old, but I believe it's the industry standard.
Thank you on that. And here's a question from Austin Mitchell. This could go to either of you. What is the EMF like in UG cables, and does putting the GCC on top of the duct bank help reduce it?
So I can field that one. Thank you for the question, Austin. So GCC, I'm assuming that we're talking about ground conductors. So what we find with underground cables is a couple of things, and we do supply studies for underground EMF. Is once we get underground, we're talking about voltage potential, right? So if you're in earth, generally you're already within a grounded surface. So when it comes to underground cables affecting somebody who's standing on the ground, there's really no electric field to be talked about, because it's all about that voltage potential differential. So you'll have potential differential between the conductors and earth, but that's usually right outside the buried conduit or the direct buried cables themselves. So on electric field, it tends to be mitigated, which is nice. Now it'll all change once those underground cables come out of the earth and then attach into the risers or the breakers that they're terminating at. And we kind of saw that in the substation EMF field example for the results. You can kind of see where those risers come up, and you can see, especially when those insulated cables are close together, there can be some severe impacts. So something to keep an eye on. On magnetic fields, however, a little bit different. So magnetic fields are not affected by anything. They pass through things, right? So we live in a magnetic field. That's how compasses work, right? And it keeps us safe from the sun's solar arrays and the solar flares. At the same time, there's magnetic field here as well that would be able to penetrate through the earth and affect, both right-of-ways and workers. What we also find in magnetic field, and this is just unique, because when you have all these conductors that are together, say you have all three phases in a conduit, and these are insulated conductors that can be very close together, and your only separation distance is just the distance of the insulation, you find that the magnetic field cancels, especially if you have all three phases together in a bundle, and your magnetic field levels can be very, very small, which is Surprising maybe at first glance, but that's a unique characteristic of underground applications. Now, that being said, if you have underground applications where you have each phase in a different conduit, and those conduit configurations can be greatly different. It can be like a horizontal configuration. It can be like a square configuration, maybe with the ground in one of the four conduits. Now you can start seeing some interaction. As those phases get spaced out, you can see pretty substantial magnetic field interactions, and it may affect things that are maybe not intuitive at first glance. So some of these underground transmission runs may run through populated public areas. They could be under streets, under sidewalks, and things like that. A lot of times when we look at underground transmission, we're more concerned about the temperature conductors and the heat dissipation and things like that. But magnetic field impacts on underground is a pretty good concern, especially since it may result in fairly large magnetic fields that are in public spaces. You got to follow up on that too. So double circuit, I think the same principles would apply. So whether you have a single circuit or double circuit, if you have double circuit and you have phases that are far apart and can interact with each other, there can be some severe impacts on the magnetic field side, not so much on the electric field side. And then it just depends on the configuration, but it's something that we can study and give you insight on a specific example. And at what length, if they're single point bonded. So with the magnetic fields, it's not the ground bonding is going to reduce your circulating ground currents. So that's good because there's danger there. But the shield wire can help us a little bit in mitigating some of the electric and magnetic field characteristics. So the bounding and the grounding of that ground conductor is important. But the main driver when it comes to magnetic field is the spacing and geometry when it comes to the phase conductors and the loading in specific. So that's going to be the main driver, the grounding and the ground conductor shield wire, depending on the application, will have some effect, but it's usually relatively minor compared to the interactions with the phases. And I see a follower from Austin just asking about whether one's in service and one's out of service. If you have a circuit that's out of service with no electric energization and no current, then I expect very little impact. You may have some coupling that you may affect on that conductor, so there may be some minor amount of current that flows. So say you have a phase conductors that are out of service and they're grounded at their terminations. You may still have some mutual coupling that drives a little bit of current and voltage, so we can consider that as well if that's the case. But generally, if you're out of service, you're not going to have the magnitudes of current and voltage that would have a major EMF impact.
We had a question, follow-up from Christopher as well for the software. So he said, I imagine that's what you use for AC interference with pipelines and rails also. Yeah, we can use CDEGS for the induced current and the voltage and the touch potentials. We use CDEGS as well for calculations like radio noise interference, audible noise interference. We can also calculate with that. It has a pretty good module for that. We were just talking about the electric and magnetic fields in this presentation, but yes, it can do that, and we can calculate those values. We can also do high voltage DC line EMF calculations. We've done a couple of those. Those are a little more specialized, and we don't use CDEGS for that, but we can do them.
Great, that looks to be the questions for now. Any other questions can be sent to Ian or William. Their email addresses should be within the bio section, or marketing@cai-engr.com. And then one last follow-up from Christopher. Does your team perform AC interference studies on pipelines and rails along with mitigation?
I can take that one, William. Yeah, yes, we do. So Commonwealth has long experience. We've been actually written some papers that kind of go over the interference problems that show up with EMF with respect to pipelines and rail projects. We regularly support that. We do use the CDEGS software in performing that analysis. And what I find when we've done some of these projects in the past is it's always challenging when you're trying to work with multiple companies. So usually we're working directly for a utility that's building the transmission line, or maybe possibly an EPC partner that's looking to build a transmission line, and they have a schedule, they have a project, they've got funding, they're really trying to push their project forward. And then we try to interface with a railroad or interface with a pipeline owner, and we find that it is very challenging to get a good point of contact with them and get the information that we need. So usually we need a lot of data around that pipeline and that rail, understand where their limits and their concerns are, and making sure that we're providing information that's valuable. And that goes to your question about mitigation. So yeah, if we have a very minor impact with that pipeline or rail, maybe there's no mitigation required. But if we affect them in a way that crosses the thresholds, then we need to look at that mitigation. I find, though, that one of the bigger challenges beyond just the technical, providing that analysis, is just the interface, is having that consistent interface with the rail company, even sometimes finding ownership if these rails are defunct or older or maybe not in frequent use can be challenging as well. So a lot of things to consider when you have a project. But yeah, if you have any projects that have pipeline or rail interference, I hope you guys think of Commonwealth as a source to be able to support you guys with engineering expertise and meet your needs. All right. Thank you very much, everyone. Thank you, Del. Thank you, William. And thank you, everyone, for attending.